you to some recent works in game theory which have applications in operating systems. Right? So not the most theoretical works, but those that have applications in operating systems. So we teach this module together with Ulrika, whom you know as well. But the division will be not half like in previous semester. I will teach most of the module, like 75%, and Enrico will teach a quarter of it. Here are our details, and we have the web page for the course as before. We will have 36 lectures, so 3 hours per week, 2 hours on Tuesday, 1 hour on Thursday. In the end, well, during the semester you will have 4 homework assignments. So these will be individual homework assignments. We will give you some exercises to do. You will do them on your own, submit them, remark them, and we will give you some feedback in class. And in the end, you will have an exam. It will be a 2 hours exam, a bit longer than the one you had last semester, but the structure will probably be similar. Well, last semester you had some questions to choose from. In this one, I think you will have one part where you will have to solve all the questions, and then also there will be some part where you will have the choice of questions to do. Any questions, please? Here are some books where you can read most of the material of the course. Actually, there will be more of it in the book than we will teach, but on the other hand, I also will cover some papers which are not in the book, but I will give you the references to those papers. So these are 2 quite recently published books on game theory, and in particular computational aspects of that. It's called Algorithmic Game Theory, and also Algorithmic Game Theoretic and Logical Foundations of Multi-Agent Systems. But the material more or less is the same, but I would say that this book is more like a handbook that has all the material systemized, and the first one looks more like different chapters that are related to the topic, written by different people. Okay, while the second one is more systematic. Then we also have a book on computational aspects of cooperative games, and the last book is about learning in games. We probably will have just one lecture on that, but there you can find more about learning in games. So these are the books, and as I said, there will be some papers to read or to see. So what we're covering is non-cooperative games and cooperative games. We'll go deeper than we did it last semester. Algorithmic mechanism design. So again, these are topics that you know what we are going to talk about, but we are going to talk about them in more detail than we did. Computational social choice, voting and iterative voting. Then we will speak a bit about learning in games, techniques like fictitious play or regret minimization when you have games played in repeated fashion. And last week we'll give provision lecture. So the course work will be 4 assignments. As I said, the division of topics probably will be non-cooperative games, cooperative games, mechanism design, and social choice. And these are the dates. Say you will have the first 2 assignments for 2 weeks. The third one, you will get it for the Easter break, but you are supposed to be able to solve it in less time. And the last one also for 2 weeks. So that's the organization part. If you have any questions on that, you're welcome to ask. not, let's get started. Say, I probably can skip this part indeed. So we talk about multi-agent systems, which is one of the fundamental topics in artificial intelligence, the application of many domains like process control and electronic commerce. And in multi-agent systems, we get multiple agents, and those agents, the software components which are self-interested, and we model the interaction as non-cooperative games. And once again, we want to know how we model the games, what will be the solution to the game, how we compute the solution, how we evaluate the solution, how good this solution can bear into other possible outcomes. And that's the well-known example. Let me skip that and we go directly to this slide. So that's prisoner's dilemma. You remember the story. We had two prisoners who are separated into rooms, and they can confess or deny the crime that they've done. And the general form of this game is where both deny the crime, they get a reward payment. If both confess, they get a punishment payment, so the reward payment is greater than the punishment payment. But if one of them confesses and the other one denies, then the confessing agent gets the temptation, the highest possible payoff, while the other one gets the sucker payoff, which is the lowest of all possible. Right? And then any game that has this structure of the payment matrix actually is a prisoner's dilemma. So it doesn't have to be the same numbers, and we had some other examples with different stories, like two students working on a project, or two firms producing the same good that they can sell for a high or low price. And the structure, the relation of the payments in that matrix is exactly as in prisoner's dilemma. So all of them are prisoner's dilemma. And what you remember from that game, that the only stable outcome for both players is actually to confess, but then both of them would get the P punishment payment, which is lower than the reward payment that both of them would get if they both deny the crime. But because they cannot trust each other, they would end up in this solution. So we talk about games in a normal form, which are given by specifying the set of players, their strategies, and the preferences of all possible outcomes, which are just their utilities. And you are all familiar with the notation: a set of players and set of strategies for each of them. There is a function that takes the profile of strategy, the combination of strategies for all of them, and gives the pair to each of the agents. Then we spoke about dominance, right? You remember strict and weak dominance between two strategies. If one strategy is strictly better than the other for all possible combination of strategies of the opponent, that strategy strictly dominates the other. If it's at least as good as the other one, but it's strictly better in at least one place, then it weakly dominates the strategy. And we would say that a strategy is dominant if it's better than all other strategies, or it is dominated if some other strategy is better than that. So there could be strategies which are not dominant and not dominated. And we know that in prisoner's dilemma, both players have a dominant strategy. To confess, dominant means that it's better for the player regardless what the other one does. But in some games, the players do not have dominant strategies, like in a coordination game, like here, both players would benefit from choosing coordinated strategies, either up, left, or down, right. But none of them has a dominant strategy here, because the choice, what's better for a given player to do, does depend on what the other one does. then we said, okay, at least we would expect the players not to play dominated strategies, right? That would not be indeed a smart thing to do, and sometimes we can solve games by iteratively eliminating dominated strategies. Here, for example, we can see that for the column player, right column strictly dominates the left column. 32 is greater than 25, 54, 26, 29, 27, so we can eliminate the left column. Then at this point we see that for the raw player, the top and bottom rows dominate the middle row, so we can eliminate that one. And now the central column dominates the right column for the column player. And finally, bottom dominates top. And here we solve the game by eliminating dominated strategies. However, you remember that in such an elimination process, the survival strategy does not have to be dominant, right? In this game, the strategy bottom for the raw player, the bottom strategy is not a dominant strategy, right? It's better to play in the central column indeed, but it's not better to play in other columns. So this is not a dominant strategy. So the surviving solution the surviving strategy does not have to be the dominant one, and then in fact in many games we may have no dominated strategies at all, so we would not reduce the size of the game at all, or we can reduce it slightly but still would not end up with a single outcome, with a single solution. Also, we may have several dominated strategies for the agents, and then we remember we had examples that if we eliminate strictly dominated strategies, then it doesn't matter in which order we do that, the solution that we get in the end will be the same. But if we eliminate weakly dominated strategies, we may have different outcomes. Right. Everyone here is able to give me an example of that now? Okay. And then we said that, okay, dominant strategies is a strict, very strong solution concept, but it does not always exist. So we need something else, and here is, and one of the central solution concepts in non-cooperative games is the concept of equilibrium, which is based on the principle of stability, and it says the following thing. If in a game some player has a strategy that gives him a better payoff than the one he is playing in the current profile, then we would say he has an improving move, and a profile that does not have such improving moves would be called a Nash equilibrium, meaning that all the agents are happy as much as they can be given the strategy of the others. Right? In other words, each player plays their best response to the strategy of the others. And here, for instance, we have two Nash equilibrium pure strategies, which is theater and football. That's a better of sexes game. So the agents do not have incentives to deviate from their strategies, given that the other player does the same. In the example where we found solution by eliminating dominated strategies, the solution we got was actually a Nash equilibrium of that game, right? How do you check that? The raw player has his maximum payoff in the given column, so given the strategy of the column player, and the same for the column player, he has the maximum possible payoff for him, given that we are in the bottom row. So we can find Nash equilibria by indicating best responses of all of the players to each other. So we can do it for player 1 and player 2, and those profiles where both of them play their best responses would be Nash equilibria. So in this game, we have 3 of them. Another example, I think we didn't have this one. Assume that we have 2 players we also want to find all Nash equilibria. There is £10 for them to divide between themselves, and the rules of the game are as follows. So each one of them has to say a number between 0 and 10, an integer between 0 and 10, and that will be their claim how much of these £10 they want to get for themselves. And now if their claim, if their joint claim is feasible, that is, they do not claim more than £10 that they have in total, then each one of them just gets what they asked for. And if they ask for more than the budget, then in case their claims are different, then the one that was more modest will get his claim, and the other one will get the rest. If they claim the same amount, then they just divide £10 equally and get 5 each. Okay? So what would be the best responses in this game? Okay. So if the other guy asks for £0, what should he do? It's written, yeah? Ask him for 10, you will get that, right? So he wants nothing. You can ask for 10, and this is a feasible claim. So you both get what you ask for, and same for until we get to £5 claim, right? If you ask for 1, you can ask 9. There will be a feasible claim. You also can ask for 10. This will not be a feasible claim. You asked for more than £10 together, but in this situation what happens? The one with the minimal claim will get his claim, which is just £1. You still will get the rest. You still will get 9. So same for 2 and 8, 4, and so on. When we get to £5, same situation. You can either make a feasible claim and get 5/5, or infeasible one, and still you will get £5. If you exceed that, so the other player asks for £6, you may ask for either 5. In this situation, you will get your 5. He will get the rest, which is also 5. Or you both ask 6, 6, and then the sum is divided equally. If he asks for 7, 8, 9, or 10, then your best response would be to ask for maximal amount, but just below his claim, so that you get what you want, and he will get the rest, because the rest now will be less than half. Right? So these are the best responses. What are the Nash equilibria of this game? 5, 6, 6, 5, right? So all those where both of the agents play each other best responses. Great. So we have games where we may have multiple Nash equilibria, or we may have games where we have no Nash equilibria at all, like in mentioned pennies. Here one of the players want to be together, another one wants to be apart all the time, and so they're never happy with few strategies. And then we play, the players would play mixed strategies, right? So they would randomize in case they cannot have an agreement in few strategies, and a mixed strategy is just probability distribution over all possible few strategies. The notion of the equilibrium is exactly the same. We replace the strategy spaces of few strategies with mixed ones, and the payoffs, the utilities of the players, with expected utilities given those probability distributions given by the mixed strategies. So the good news that in mixed strategies we also have a Nash equilibrium, where the game has a finite set of few strategies, and that's the main result of Nash, for which he got his Nobel Prize. Let me tell you now why that theorem is true. Okay, we are not going to do the formal proof in all detail, but just for you to understand the idea. So most theorems of the existence of some stable solution are proved using so-called fixed point theorems. Does everyone know what a fixed point? Okay. So if you have a function, okay, on a particular domain, and in that domain you have a point, so that when you apply the function on that point, it returns the same point. That point would be called a fixed point. That means that if the function got there, it will never leave that place. Okay. That, in a sense, meaning that the function found its stability point. Okay, that's fixed point. And there are a few fixed point theorems given the behavior of the function, given the domain on which the function is defined, and so on. One of them is Brouwer's fixed point theorem, saying the following thing. If we have a function which is continuous, and its domain is convex and compact, do we know what convex and compact is? Convex, I hope we do. Yes, no? Convex functions? Convex sets? Well, just intuitively, I can. Do we have it? A convex set is a set where if you take 2 points, okay, I'm just giving the intuitive definition of all the definitions here, and you take the interval between those points, all the points in the interval belong to the set. So if I had a set like that, oh, sorry, this point has to be there. This would not be convex, right? Because the interval is not fully belongs to the set. Okay, so convex sets are of that form that for any 2 points, the line that connects between them also belongs to the set. So that's convexity. Compact means that in some, so it doesn't have to be a finite set, it may be an infinite set, but it's something that you can cover with a finite number of, well, let's call them balls. Okay, so somehow it means that a compact set is bounded. Right? So it's not precise what I'm saying, but just for you to have the intuition about what's convex and compact is. Now, why is this important for us? Because when we look at the set of mixed strategies, okay, what is the set of mixed strategies? We have our pure strategies, which are points in Rn, right? And mixed strategies are probability distributions. So in fact, so we got pure strategies, and then we have all possible probability distributions. So all the space that connects between them, where those points are the extreme points of the set. Okay, so this set is convex and compact by definition. So it's compact because we had only finite number of points, and we took the probability distribution in between. So we can sort of, cover the set with the finite number of balls that just cover those points, and it is convex also by the definition because we included all the intervals connecting between any 2 points in there. So we have our domain, which is the set of mixed strategies, and it's compact and convex, as that theorem wants us to have. Now, let's define some function on that set, and we define it in the following way. So we want it to be continuous, so that we can use the fixed point theorem. How we define that? So we take the point in our space. The point in our space is what? A mixed strategy profile. Okay. So we take a mixed strategy profile and we map it to something that shifts every mixed strategy for each one of the coordinates there. A coordinate there is actually a player, right? So that's mixed strategy of player 1, 2, and so on. And we shift it slightly, and we shift it in the direction of his or her best response. Okay, so we improve for that player. And the function is continuous. Okay. Now, the function is continuous, the domain of the function is convex and compact. That means that the function has a fixed point. Right? So what does that mean? When we are there, we do not move from that point. Okay? But the moving was defined in a way of improvement for the players. So if we know that there is a fixed point, that means that we cannot move, but by definition of our function, we cannot improve for any one of the players. And that's basically the definition of Nash equilibrium. Right. So that's the idea. Formal definition is a little bit technical, but you have the idea of that. Now, how easy that you compute Nash equilibrium in general? So the complexity of computing Nash equilibria is hard, but hard is not an usual way. So I would suppose you all are familiar with the notion of NP-hardness. Right. So this class of problems, finding mixed strategy Nash equilibria, is somewhere in between of polynomial time, so it's more complex than polynomial time, but it's easier than NP-hard. So they're not NP-hard, okay, but they're not polynomial. And the class is called PPAD, which is come from the name of a particular representative problem of that class. It's called polynomial parity arguments on directed graph. That's a particular combinatorial problem on graphs, which is taken as a representative of that class, and by which to which one we compare the complexity of those problems. I'm not going to talk about that in very detail. There are two sources where you can read about those things if you're interested in computation of equilibrium in general games. There is a chapter in one of the books that we gave, and there is also a survey paper by Kostis Daskalakis about computation of Nash equilibrium. What we've done so far, we just computed mixed strategy Nash equilibrium in very simple games, 2-player, 2 strategies. And you remember how we've done that. On Thursday, I'll show you how to compute Nash equilibria in games with 2 players, but general number of strategies. We didn't do it last semester. But we probably will not go beyond that, because the problem is not easy. So to remind this, when do players play a play strategy? If they are indifferent between playing their pure strategies. Right? Otherwise, they would just choose the one which is better. So assuming that we have 2 players with 2 strategies each, the first one plays his strategies with probability is P and 1 minus P, the other one is Q, 1 minus Q, right? Then the expectation of the utility for the second player would be given by P, his utility in this profile, plus 1 minus P, his utility in this profile. That would be his utility from playing his first pure strategy. And this has to be equal to his expected utility from playing the other strategy. Right? So to compute the probabilities of the first player, we compare the utilities of the second player. Right? And you remember the example that we had with stack hand, that if I change now the utility, so the mixed strategy Nash equilibrium here was 2/3 for the first player and 2/3 for the second player playing his first strategy. And if we change the utility of the second player here, it affects the strategy of the first player, or the other way around. So we have the change for the first So this is all we talked already about. We will speak about other solution concepts. We started to talk about maximin strategies last semester. We also will talk about minimax strategies, which is something different but very related to maximin. Then we will speak about rationalizable strategies, which is another concept of what is reasonable for players to play in a game. We will talk about correlated equilibrium, which does involve probabilities, but not over pure strategies, rather about of the joint strategies of all the players. Okay. And we will also talk about absolute Nash equilibrium, which is in a way some approximation of a Nash equilibrium, and strong equilibrium that talks about stabilities of coalitions, groups of players, rather than individuals. Okay, so let us get back to maximin. So remember what's that, right? Maximin strategy of a player is the, in other words, the safety level strategy of a player. That's how much, that's a strategy that guarantees the player a particular payoff, given that all the others want to punish him. Okay? But the process of punishing is going the following way. So when the others commit to their strategy, no, the other way around. So the player commits to a particular strategy, and then the others choose the worst possible strategy for him, well, profile for our player. Okay, so we take maximum over the strategies of the given player and minimum over all possible combinations of the others, given his utility. Right? So maximin, me as player I look at my utility, okay, and I want to choose the strategy for myself that will guarantee me maximum possible payoff, given that the others are all against me. Okay. And we found maximin strategies in pure strategies only so far. But generally, that can be a mixed strategy. Okay, we will see now an example. And the safety level, or the maximin value of the game, would be that very utility that our player gets when he plays his maximin or safety level strategy. Okay. But once again, generally, that does not have to be a pure strategy at all. So the intuition, once again, is we have our player that has to commit to play in a particular strategy. So he chooses his safety level strategy, and then the others play whatever they can do to punish him as much as possible. Okay. So what is the best thing that player can do? In prisoner's dilemma, what would be the safety level strategy for each of the player? So in pure strategies, we may see that so if we are the raw player, then if we play deny, the worst possible K for us would be -10. If we play confess, the worst possible case is -5, right? -5 is less painful than -10, so we play confess. And there is no better mixed strategy safety level strategy here. So the safety level would be given by pure strategy, and that's because we have dominant strategies in this game. Okay. I will show you later how to compute mixed strategy safety level, and you can check that in this case we will just not have the solution to that. So it has to be the pure one. So what is a minimax strategy? Minimax strategy has another meaning. So it's sort of a dual strategy in the game. There will be errors in that slide, so I first want to explain that and then show you the error. I will fix it.
For finding my minimax strategy, I'm looking not at my utility. I'm looking at the utility of the other player, and I want to punish that player. Okay. So the minimax strategy of a player is the one where we want to punish someone. He will play their best response to our punishment, but here the process is different, the order of actions is different. We assume that we commit first to our punishment strategy, and then he best responses, as opposed to Maximin. Okay? In the Maximin, we had, as the punishing players, we had more power than in Minimax, generally. In two-player games, you will see that brings. So in two-player games, there's an error in the formula, so let me just give you the definition and I will tell you what's wrong there. So in two-player games, the minimax strategy for player I against player minus I, the opponent, would be strategies that keeps his maximum payoff at a minimum. So if I am player I look at the minimum of the maximum. So he would choose the maximum of his payoff over his strategies. I will choose minimum of that over my strategies. The utility of there should be of player minus I, not of I. So once again, we want to consider the amount by which we can punish other player, but we must commit to that strategy first, and such punishment can arise in repeated games a lot. So what happens when we have more than 2 players in a game? What would be the minimax strategy? How we define that? When we have 2 players, it's easy to say, right? So I'm just playing against the other one. When we have more than 2 players, we will. It's not easy to define that in that way, so we actually need all the players to gang up against a given player. Okay? So let's fix some player J, and then all other players minus J, in this case it will be not just one opponent, but a coalition of all other players. They will choose some joint strategies so that to minimize the payoff of player J. And then the minimax strategy of some given agent I would be his component on that joint strategy. Okay? So once again, we have player J, that the player that all the others, all minus J other players, want to punish. They want to minimize his payoff. Again, that should be UJ, not UI. And then they choose a joint strategy that minimizes his payoff, and the minimax strategy of some given player I, who is not J, would be the ith component in that joint strategy. And that before, the minimax value for player J would be the payoff that he gets there. So again, the intuition is, again, we have players punishing other player, but here they commit to their strategy first, and he best responses. In Maximin, he first chooses his best response, and then the others punish. Now, Maximin and Minimax are very related notions in games where we have only 2 players. And that's very convenient for computation issues. So in 2 players game, in fact, the minimax value and the maximin value of the player are always the same. So it doesn't matter in which order they commit to their strategies, they will get the same thing. If we have a game where there are more than 2 players, then we have a weak condition saying that a player's maximin value is always less or equal than his minimax Why is that intuitively? So what's my maximum value once again? I commit to something. I commit to a strategy, and then the others do what they can to punish me. In Minimax, they first commit to a strategy, and then I react in my best possible way. In which case do I have more power? In the second case, right? So you would expect that the Minimax value would be at least as good as the maximum value. Okay. And so for 2 players, there will be the same one. For more than 2 players, it may be different, but that's the relation between them. I'm going to prove that. It's not a difficult proof, but a little bit technical and boring, so would you like to have a break, or shall we go on? Say anything? Continue? Say, what's also special about maximum and minimax strategies? Those strategies actually depend on the payoff of just a given player, right? So for maximum strategies, my maximum strategy depends on my utility function. For minimax strategies, the strategy depends on the payoff of the on the utility function of the other player that we're all going to punish. Right? So it actually does not depend on the utilities of the other players. And that gives us the combination, the profiles of strategy where every one of them can play their maximin or minimax. So for 2-player games, we have, again, this special case that minimax and maximin are the same. And why is that? So if we look at a particular subclass of 2-players game, which is called constant sum. Constant sum means that we now have only 2 players, and the utilities of these 2 players is the sum of their utilities is always some constant c. And if this constant c equals 0, then it's not just a constant sum game, it's a zero-sum game. And the zero-sum games are a very special class of 2-player games. So what happens there? In fact, you have a pure conflict between the 2 players. When one has a positive utility, the one has the very same utility but negative. I'd say there is a clear conflict between the 2 players. One wins, another one loses. Exactly the same amount. I'd say it's like one of the players pays from his own pocket to the other one. And in those games, there is a tight connection between minimax and maximin. And also an Nash equilibrium of that game. Why is that? Let me tell you why is that, and then we go to the theorem. So we said that to compute maximin or minimax, we look at the payoff of a fixed player, and we don't care about the payoffs of the other players. And that's why if we have a game of 2 players, then we always can ignore the payoff of the other player. Right? So we can replace that game with a zero-sum game. We can replace the payoffs of the other player, which are irrelevant, with just negatives of the payoffs of the other player. And then we have a special class of zero-sum games. And in zero-sum games, what we have is that in any Nash equilibrium, each one of the two players that we have would receive a payoff that is equal to both his maximin and minimax values. And more than that, actually, the set of strategies, the set of minimax and maximin and Nash equilibrium strategies of the player will be the same set. So in fact, for zero-sum games, well, actually, any finite two-player game, the maximin, minimax, and Nash equilibrium strategies, I'm talking now in mixed strategies, would be the same. Okay. So why is that true? Again, we are going to give just the idea of the proof, but we will understand the intuition behind this. So we know by the Nash theorem that there is at least one Nash equilibrium in mixed strategies. So that exists. So let us have one of them. So let us fix some Nash equilibrium S prime. Okay, and let's fix player I there, and his payoff in that Nash equilibrium is VI. Okay. Now let's his maximin value be upper by VI, and the minimax value the lower by VI. What we want to show is that all these values are the same values. Say, let's show for the maximin value first. First of all, it's an easy observation that it cannot be the case that the maximin value of the player is greater than his Nash equilibrium value, because otherwise player I would just deviate to his strategy that gives him the maximin value, and that violates the definition of the Nash equilibrium. Right. So it can't be that V bar I is greater than VI. So we now have to show that that it actually greater or equal than that. A bit of notation. So what do we know? We know that by definition, the strategy that the opponent player, minus I, plays in our given Nash equilibrium profile is their best response. Right? So the value of the opponent player is the maximum of his utility over all his strategies when player I is fixed to his strategy S prime I. Okay? And equivalently, we just multiply that by minus. So if V minus I maximizes the utility, then minus V minus I minimizes the negative of the utility. Okay. But now we know that the game is zero sum, and that means that the negative utility of player minus I is actually the original utility of player I. Okay? And the value, the negative value of minus I is actually the original value of player I. Okay? And that's why we get that VI actually minimizing his utility over all possible strategies of the other player, right, in our given profile. Okay, and now what? Now the maximin value is to take maximum over all strategies of player I over that very, over that very amount, right? That's the minimum over the over the strategies of the others of my utility, right? And I take maximum of that over my strategies. That's exactly the maximin value, right? So that means that the maximin value is greater or equal than that. That thing we just shown to be exactly the value of the Nash equilibrium for player I. Okay. And for Minimax, I will save it. It's just the same exercise. So we have, in general, that the maximum value, the maximin value and the minimax value of a player in two-player game would be the same, and that's why we can just define the value of the game by fixing it to be the value of one of the players, say player one, role player. Okay. Now, the theorem actually is more general. It gives us that the sets of maximin strategies and minima strategies are the same, and actually any maximin strategy profile is a Nash equilibrium in mixed strategies once again. Now, what happens in some games that we are familiar with? In matching pennies, you remember that the Nash equilibrium was for both of the players to randomize equally between the two strategies, so that the only Nash equilibrium of that game, and that would mean that that's the only maximin and minimax strategies for both of the players in mixed strategies. Well, we remember that in pure strategies, they could not guarantee that value to themselves. So the value of the game would be 0 here, which is the value of each one of the players in the Nash equilibrium. Now, having this minimax and maximin theorem, we can actually compute mixed strategy, maximin and minimax strategies for any two-player game, not just zero-sum. By remembering the fact that, once again, maximin and minimax strategies depend only on the payoff on the utility function of a fixed player and does not depend on the utilities of the others. So that's why we can replace their utilities, the utility of the irrelevant player, by exactly the negatives of the utility of the fixed player and turn the game into the zero-sum. So we take the game, so if I want to compute the maximin strategies, okay, I'm player I need to keep my utility function as it is, and for the other player, I replace his utilities with just negatives of mine. Okay? Then what I do? Then I just find a mixed strategy Nash equilibrium in that game. We know to do that. Okay? And the Nash equilibrium strategy in that game will be my maximin strategy in the original game. All right? If I want to find the minimax, then I need to turn the game into a zero-sum game where I keep the utility of the other player as in the original game, and I replaced my utility function with the negatives of that. And again, I just compute the Nash equilibrium of that, and that would give me my minimax strategy in the original game. So if we look at this variant of the game of Battle of Sexes, we have two strategies for each of the players. They get zeros if they do not coordinate, or they get 2-1 for going to theater together, or 1-2 to go into football together. So what happens in pure strategies? Let's look at the maximin strategy for both the players here, or player one, in fact. So if he plays theater, then the other players would give him the utility of 0 by playing football. If he plays football, then the other player will punish him again with the utility of 0 by going to the theater. So in pure strategies, player 1 can only guarantee himself the payoff of 0 in this game, because he has to commit first. Right. But if can increase his safety level payoff to 2/3. Okay, so let's compute that. So I want to compute now the maximum strategy in mixed strategy for player 1. So maximin, once again, I care about my own utility, so I replace the game with the zero-sum game where my utilities are kept as it is, so it's 2, and the other one gets the negative of that, -2. 0, 0 is the same. There I keep 1 for myself, the other one gets -1. And let's find a Nash equilibrium of that. So if I play B1 minus B, and I look at the indifferent point for the other player, then it will be, he gets -2 with probability P, 0 with probability 1 minus P, and that should be equal to getting 0 with probability P, or -1 with probability 1 minus P. Okay. So we get that goes there, that goes there, we get 1 equals 3p, p is 1/3. So that's the Nash equilibrium in the zero-sum game, and that's the maximin strategy also in the original game. Okay. Now, how much does this player get when he plays this strategy? Say, his expected utility would be having, so he would get 2 with probability PQ, so P is 1/3 Q, right? Here there are zeros, and he will get 1 with probability 1 minus P, which is 2/3, and 1 minus Q. Right? So we have 2/3 Q plus 2/3 1 minus Q, so that's 2/3 Q plus 1 minus Q. 2/3. Okay. So by playing a mixed strategy, the player can increase his safety level. Are you still with that? Sorry. So if we got to, yeah.
Please, what does it mean that the second player will get 2 by probability BQ, not just Q?
Well, what's the definition of the expected utility? It's how much you get. You take the probability of the joint profile. The probability of this profile is P and Q. Of that one, P, 1 minus Q. Of that one, 1 minus P.
So why for the first player we solve it for 1 probability, which is P?
Well, when we are looking for this thing, what we're doing, we are comparing playing the pure strategy for the second player and the second strategy in pure, right? So you will take
He will win 2 by probability of
yeah,
P.
it will be the very
Right.
same thing. So you could have written it with Q's, but they would just cancel. So in fact, yeah, the expected utility would be indeed minus 2PQ plus 0, 1 minus PQ again, right? But that's the same Q. Okay, say it's just like Q multiplied by the whole thing. And we just want to compare the utility of playing the two strategies. if you, like in those indifferent points, if you look what is, say, you get now that the utility here of the second player, the expected utility in these indifferent points is either minus 2p or minus 1 plus p, which is minus 2/3. Okay? Now, if you compute that utility, okay, so what's the real utility there? It would be, so you have to compute q as well. So if you compute then the expected utility given both p and q, you will get the very same number. So now if we want to compute the minimax strategy for the first player, what do we do? So in minimax,
Do you make another zero-sum game, but where you keep the other player's utility
yeah,
the same?
exactly. So now we care about his utility function. Say his utility function is 1. We have minus 1 here, and here it's 2, so it's minus 2 for us. And again, we find the Nash equilibrium of that, and that would define the minimax strategy for player I, the raw player. I didn't think we would go that fast. I did prepare more slides for today, so yeah, because I expected a couple of students that didn't take the first semester, and so I'm happy to answer any question on that, or yeah.
I had a question. Maybe everybody is interested about the feedback for classes. This way we have a look at my
Feedback, you mean the coursework or everything? Well, so coursework is not marked yet. Exams, Enrico has marked his part. I haven't marked my part. So that's why I can't say much.
But just this work, can we have a look when it's ready?
Well, the deadline for the marks to be released is 4th of February, so we will get them. So we submit the marks on 4th of February. Shortly after that, you get them released. I probably will have more to say on Thursday because I'm planning to mark them today, tomorrow. So, but I would expect you to have done well. Any more questions? Any? So is that all clear? All right. So next time, yeah, I'll get more material ready. Sorry, I didn't estimate my time well. Next time on Thursday, we are going to talk about rationalizable strategies and other solution concepts, and probably also about computing Nash equilibrium for two-player games with more than 2 strategies. And then after that, we move on to particular game classes and some recent results about them. So less theoretic stuff, more applications, but still there will be some things to solve. Okay. After 2 weeks, you will get a homework assignment, which will be on non-cooperative games, and you will have 2 weeks for that. So then, yeah, I'll say goodbye for now, and I see you Thursday. If there are any comments.